Okay, good morning, guys. All right, the announcements are pretty simple today. Got a homework assignment due on Tuesday, and we're going to continue talking about Chapter 5 stuff, look at kind of an interesting engineering application of the continuity relationship. Before we get into it, any questions? Anything at all? Questions from maybe the last class or from the lab? Yes? Mm-hmm. Are you talking about which experiment? The orifice experiment? 2? Yeah, that's probably too high for a coefficient of discharge. Yeah. Yeah. I'd have to look at the calculations to try and help you make sense of that, but that's not within the realm of what might be considered typical. Yeah. Okay, well, remember last time we looked at this tank, and we had the idea of a system is a continuously connected body of particles. And the system can change location over time, but we call it the system just for purposes of tracking. We define where our stuff is that we're going to be calculating. And it's showing it kind of as a continuous plug that isn't mixing with the fluids on either side of it. Now in reality, particularly because of turbulence in the pipe, there would be mixture between fluid particles. But this can be minimized in some ways. You may not be aware of it, but there are pipelines going all across the United States that are transporting diesel fuel, crude oil, finished gasoline, and they'll put different things inside of those pipelines. And so they may have, a mile in the pipeline, a mile of diesel fuel, and behind it would be gasoline. And it's just that the fluids move so slowly through the pipelines that they don't mix very much. So it's kind of an interesting thing, the plug flow idea through pipelines. We'll talk more about plug flow in environmental engineering. But for today, what we're going to do is look at this Reynolds transport theorem. Now last time I told you what the variables CV and CS stand for. Anybody remember what those two are meant to identify? Very good, that's right. So the control surface is on the outside area of what's enclosed inside is the control volume. Now here, the V that has a cross through it, anybody remember how that's different from the V without the strike through it? Yeah, exactly. So the strike is volume, the V without the strike is velocity. So let's look at what this equation is trying to tell us. It says something control volume, volume times density. All right, so what that's saying is if you multiply volume by density, it's a certain amount of mass. And so it's saying inside the control volume, we can keep track of mass over time. So here's our control volume. So the tracking of mass over time is just about accumulation inside of that tank. Now the second term is saying something about the control surfaces. What's V times A? V times A, it's flow rate, Q, volumetric flow rate. So you'd get cubic meters per second, for instance. But then when you multiply it by density, do you remember from the last class meeting what density times Q is? What variable we use? M with a dot, that's right, mass flow rate. So that's saying you can keep track of the mass flow rate through the control surfaces. And when we combine the two terms together, it's saying keep track of the storage and the transport in and out of the storage through the control surfaces. And when you combine those two things together, you can know the change of mass in the system over time. Now, for fluid mechanics, we're going to assume that there's no reaction happening inside of that storage tank. But that's not always true. There will be chemical reactions in some cases if it's a vessel designed for that. More typically in civil engineering applications, we may have a biological reaction happening inside of a tank. And an example of that is activated sludge treatment of wastewater, where inside of a tank there would be bacteria that are breaking down pollutants. And that's the technique that's used all across the country as the main line of defense for preventing pollution in rivers, is we'll load up a tank with wastewater, encourage an environment where bacteria can grow, and then pollution comes in, there's a consumption reaction inside of the tank, and cleaner water comes out. You wouldn't want to drink it necessarily, but it's fine to put into a river. And so this Reynolds transport theorem is robust enough for us to keep track of not only conservative situations where there's no reaction happening, but also a situation where something is either being created or destroyed within the system. We could say over time how much the mass is changing. So here are some variables we need to keep in mind. M is mass, density, volume, velocity, area. Okay. So the Reynolds transport theorem, it relates storage versus transport and mass accumulation. However, most of the time, we're going to say that there's no mass being created or destroyed in the control volume. Now you may think, well, mass can't be created or destroyed to begin with, but there's different types of mass in the world. And so we could be talking about the pollution that comes into a wastewater tank, and the way the pollution is broken down is that bacteria eat it. It's their food. And so the mass of bacteria is increasing as they eat the pollution, and the pollution mass is decreasing. And so it's more of an exchange of one form of mass into another. So let's just say in fluid mechanics, we're not going to go into too much detail about activated sludge. And so we're going to assume that the change of mass is zero. So the left side of that equation, the left side of Reynolds transport theorem, if we say that there is no change of mass because there's no reaction, then the accumulation in the control volume has to be accounted for by the flow in and out through the control surfaces. In other words, we can explain what's going on inside of the tank in terms of how much mass there is in the tank by just looking at in versus out. We couldn't do that necessarily if there was a reaction, a biological reaction happening in the tank, because in and out would tell you part of the story, but then another part of the story would be what's happening in the tank. Here, we've set that reaction term equal to zero. So we have the accumulation term, and so why is it accumulation? It's because we're talking about volume, changes of volume over time. So the liquid level increasing or the liquid level decreasing, that's the volume side of things. And then CS, we call that our transport term. It's the net mass efflux through the control surface, because if we go back to the idea of the storage tank that has some water in it, here our control surfaces are the pipe surface in, the pipe surface out, and we would simply need to know what's the velocity. We'd want to know the area of that, and then the density of the fluid. And so knowing velocity in, velocity out, the density of the fluid, we could say that if you have a net positive transport, then you'd expect there to be a net increase in the control volume, the amount of mass inside of the control volume. So all of this is just really kind of overcomplicated ways to say that accumulation is in minus out. All right. Or in other words, that the change in mass inside of the control volume over time is just the mass flow rate in minus the mass flow rate out. So how many kilograms of water is in the storage tank? If we track the mass flow in versus the mass flow out, then we can know the rate of change inside of the control volume. Deceptively simple. It's simple but important. Okay, let's change gears a little bit. Last time we talked about intensive properties and extensive properties, and one of the ways that we apply that information is in finding pressure. One of the ways that we can find pressure if a pipe diameter is changing, what's this blue line? What do you think it's meant to represent? It's a streamline, right. And so it looks like whoever's setting up this problem is already on the right track because they have picked 2 points that are on the same streamline. So what does that tell you? What equation is probably going to be applied here? When was that an important consideration of ours? Bernoulli, right. Remember, the assumptions behind Bernoulli's equation was we apply it along a streamline for an inviscid fluid, meaning a fluid with no viscosity, an incompressible fluid, and for steady flow. So here we see that Bernoulli's equation comes from integrating Euler's between 2 points. You can apply it if the flow is steady and know the change in pressure, but the problem in a case like this is the path lines are always shifting. There's lots of them, and especially if conditions are unsteady, it becomes really challenging. And so rather than applying the Lagrangian approach, Euler's approach is dividing areas up into small cell elements. And we would say that whatever's happening to a fluid at one element, its properties are transported through the element. So we're talking about the Reynolds transport theorem. Whatever momentum, for example, comes into an element must go out of an element unless that momentum is stored inside of the element. So momentum is a property that's related to mass, and so the properties go with the mass itself. So you can apply the free body approach to each one of these elements, and there are computer programs that do that, and they take the pressure measurement at one location and an understanding of what shear stress may be due to roughness of a pipe wall, and then they apply the Reynolds transport theorem just to say if there's a certain amount of pressure at a location, what are the resistive forces on either side of that fluid element. And so the Reynolds transport theorem allows us to take this complicated approach where there's just too many points and apply it into an environment where we've developed a mesh to describe the flow field. All right. Well, here is an illustration of a problem where what we want to know is what's happening inside of the control volume. The control volume is enclosed by the control surface, and we note that looks like water's being poured into what's an open tank. The clues that this is a tank that's open to the atmosphere are these little dashed lines near the water surface that are meant to illustrate ripples at the water surface. Now, the water that's pouring in, the diameter of that stream is decreasing. Do you know why? Why it was wider at the top and it's getting narrower towards the bottom? Velocity, yeah, velocity is changing. When you pour water out of a pitcher, for example, when you first start to pour it, it has a downward velocity of 0, but it starts speeding up because of gravitational acceleration. And so here, the way that continuity is satisfied, remember we know that in has to equal out, so you can't have the cross-sectional area be the same here where the water velocity is slow compared to here where the water velocity is fast. As it speeds up, it contracts in diameter because the flow rate needs to remain the same. Q has to be the same, and remember Q equals VA. So the flow rate Q is the same here at the top of this stream as it is just before it comes into the tank. The Q is the same, and so if the velocity increases due to gravity, then the cross-sectional area has to decrease, and that's why the diameter is narrowing. So what they've done is they've identified a point here at the control surface where we know both the velocity of the fluid that's pouring into the tank and also the cross-sectional area. There's another part here at the bottom of the tank where this is not a free jet of water coming out, but rather what it is it is a pipe that has some sort of a valve control downstream that's fixing the outlet flow at 0.003 cubic meters per second. So what I would like you to find out is if the tank diameter is 0.5 meters, and by that what I mean is this is a circular tank that we're looking at. It's not rectangular, it's circular, and then the diameter is 0.5 meters. How quickly is the water level either rising, falling, or is it a case where it's going to stay steady because the flow in equals the flow out? Let's apply the Reynolds transport theorem in terms of mass flow to find out what's happening to the liquid level over time. Okay, so we start off with the preliminary stuff. If you're given the diameter of the tank, you know probably you're going to end up needing the cross-sectional area. So calculated that. And then we're looking at in and out. The in is given in terms of velocity and cross-sectional area, so we find the volumetric flow rate in. And then, since we know the density of the fluid, we can also calculate the mass flow rate in, 17.5 kilograms per second. When it comes to the flow rate out, it's already given in volumetric terms, so all we have to do is multiply that by density, and we'll get 3 kilograms per second flowing out. So then the net accumulation of mass inside of that tank is 14.5 kilograms per second. So it's going to be getting heavier and heavier over time. Now, as for the fluid level, it's going to be rising since there's a positive accumulation, and the rate of the rise we can calculate just by, I guess, converting it back into volumetric accumulation by dividing the density. And then if we know that Q equals VA, it's a velocity that liquid level is rising. And so the Q accumulation is just the difference between what's coming in and what's going out. So that's going to explain how much volume is added every second. And if we know the surface area of that tank, then we can divide and find out what the velocity of the rise is going to be. And so it's going to be rising very slowly, 0.0738 meters per second. Any concept questions or any issues you faced as you did that?
So for this, wouldn't the density just cancel out?
Yeah.
That's
That's right. You could have solved this without considering the density at all. You know, if it was a positive volume accumulation, that would have told you that the liquid level is rising. You didn't have to know the mass rate that it was accumulating to be able to predict that. And so, yeah, the mass component of this example is just to kind of reinforce in your mind how to calculate mass flow. It's not necessary. All right. Now, I want to ask you something. Look at this reservoir. There's a certain amount of water in the reservoir already at this current point, and we're adding additional water due to this plunger B. It's like a piston that's going towards the reservoir, and what we know is the piston has a diameter of 6 centimeters. And so it's moving at some velocity v. We don't have the actual quantitative value for that. So it's 6 centimeter diameter and it's going in at v. Well, there's flow coming out of the reservoir because piston A is retracting. And it's retracting at twice the velocity that the other piston is going in. But it only has half of the diameter, 3 centimeters versus 6 centimeters. All right, so one's going in, one's going out, double the velocity, half the diameter. So what's happening to the liquid level here? Oh, I love it when people fall for my trick. Is it staying the same? All right, it's squared. Why do you say that?
when you're doing the area, the diameter should be squared.
That's right. Exactly. Yeah, so the diameter, that's a trick, right? Because remember, Q is VA. It's not V times diameter. And A is pi d squared divided by 4. So his point is that if you have double the diameter, that means you've got 4 times the area. So although this one is only moving half as fast in terms of velocity, the double area means that the liquid level is going to be going up in that problem. And so we could prove it to ourselves in this way. We could calculate the area of both of those plungers and calculate the flow in terms of this unknown variable v. It could be any velocity, really. But if we multiply the velocity times the cross-sectional area of that cylinder at B, then that'll tell us the flow rate in. And then if we look at the flow rate out in terms of V, it's half that. Because although the velocity is double, the area is 1/4. So then the net, if we have in minus out, obviously there's going to be more in. So that means a net accumulation inside of the control volume. And, you know, this is water. We can put in the density if we'd like. But here it's saying that the accumulation is the density times the velocity, and then 14.136 is the difference between the in and the out. So another successful semester of my trick question, finding at least some takers. I love it every time. I'll put all the rest of my trick questions into the exams, though, so for maximum enjoyment. You wouldn't enjoy that? Well, I'll take them out then. Why has nobody ever told me that before? All right. I'm glad we sorted that out. Man, I'm a bad judge of what students want. All right. One more example. We have a water pipe. It's filled with water, and we have like a metal cylinder falling downward in the center of this cylinder. This is kind of a little bit similar to an earlier problem we had. Remember, there was a pipe and there was some oil lubricating it. Well, that was a shear stress problem. This is a continuity problem. What we know is that this metal cylinder is falling downward at 1 meter per second, and the diameter of the pipe is 200 millimeters. The diameter of the cylinder is 150 millimeters. What we're interested to know is the velocity in the water in the space between the cylinder and the tube wall. So here's the cylinder, here's the tube wall, here's the space I'm talking about. So how is this a continuity problem? Why am I showing you this example on the day that we're studying Reynolds transport theorem? What we could say is that when this cylinder goes down, it's pushing the water someplace. I see Stuart nodding his head. Where is it pushing the water? As it goes down, you know, that solid cylinder is displacing some water. So where does it go? It's got to go around the sides. Exactly. So in this problem, the way to solve it is look at defining a control volume. So you draw a control volume, and then you say, how is fluid going into the control volume? How is fluid going out of the control volume? And then what we're trying to find is the velocity in this space between the cylinder and the outside pipe. So part of the problem here is just interpreting the problem statement. Part of the problem is trying to visualize what this looks like in 3 dimensions. And then the last thing is identifying where your control surfaces are going to be so you can look at the in versus the out. All right, I'll give you a moment to think about that, then I'll draw a couple of clues on the board. For the outflow? It's the cylinder area. So the cylinder's falling downward. The outflow area is just the edge around the cylinder. All right, so the tricky thing here is figuring out where's the water coming in and where is it going out. So the cylinder going downward is forcing water into this control volume. So the water enters that control volume at a rate that's equal to the area of the cylinder multiplied by the velocity of the cylinder. Those two things will give us how many cubic meters per second of water is being forced into the control volume by the cylinder. Now that same amount of water has to go somewhere. It goes around the outside of the cylinder. It can't flow through it, and that's not like a circular shape on either side of the cylinder. To visualize it in 3D, what you've got is a ring-shaped or a donut-shaped element where the cylinder's going down and the water is going up around it. That's the only place the water can go, is this area. And so the way that you find that area for the flow out is just the difference in the overall pipe area and the cylinder area, which is where it can't flow. So the flow in is 0.01767 cubic meters per second when we multiply the velocity by the area of the cylinder, which is what's forcing the water downward. But then that water is going to have to flow around the outside edge, and so this shows the net area. So this 0.013746 is the net area on the outside of the cylinder. It's the difference in the two circles. And so we know what the velocity has to be because we know the flow rate going through that space, and we know the area of that space. So Q divided by A will give us V. And that's where 1.29 meters per second comes from. So what's the tricky spots of this problem? When you're just starting with the picture from the example description, the tricky parts are maybe visualizing this in 3 dimensions, knowing where to put the control volume. You know, I drew it on the whiteboard there, but you have to think about where you put the control volume. It should encompass where something is happening. You know, it should reflect where the water is being pushed by this incoming cylinder and where the water is exiting around the edges. And so if we drew our control volume to enclose the entire system, so let me raise the whiteboard, the projector screen, and show you what a really useless control volume would look like. If I had said, my control volume is this, if I put the control volume around the entire cylinder, nothing's happening here because the water that gets pushed out of the way, there's like no net change if you take the entire control volume. There's no flow. There's no water flowing through the pipe. The only water movement is caused by this falling cylinder. And so this control volume, it wouldn't quite capture the essence of what's happening. But if we change the control surfaces to say, well, we need to cut through this surface because that is where something's happening. That's where the flow is going out. And the same on the other side, we need to cut that surface because that's where the flow is going out. And then we think in 3 dimensions. Well, that's not 2 sides. That's really one continuous ring. Okay? So that gives us the outflow, and then the inflow is just going to be that cylinder. Now, solids don't flow, right? There isn't a flow rate of a solid. But the cylinder falling downward is pushing the water that's in front of it at a certain flow rate. And so that's why we can apply continuity equation to a solid like a cylinder that's falling down through a fluid. It's having an effect of pushing water at a certain flow rate Q. All right? Any questions from this example? Let me bring the solution up one more time, just in case there are any specifics with the numbers. All right, so flow in, flow out. Difference between the two will give you the velocity. Okay. Has anyone already started on the homework? What I usually do, you know, is I like to give you a couple of key ideas on Thursday so you can have them percolating in your mind before you do the homework over the weekend. But I didn't do that today. I ran out of time. I was grading exams in 221. You guys took some of you took the exam yesterday. So you're kind of on your own as far as homework goes, is what I'm saying. But if I remember correctly, I constructed this example with something specific in mind, so hopefully it's a good one. If you've got questions, of course, saying you're on your own is a little bit counterintuitive because we're not done, by the way. Yeah. You know, there's also sending me questions by email and coming by my office hours. So, all right. So, in the orifice lab that we did, the water level was constant. We can use the continuity relationship and the Reynolds transport theorem to look at what happens when the liquid level is falling. So here's the orifice equation, square root of 2gh. Where does that come from? Do you remember from whence it is derived? Bernoulli's equation, right. What we do is we say, let's consider the surface of a tank and say that's location 1, and the jet of the water that comes out and say that's location 2, so that we've got two spots that we're going to apply Bernoulli's equation to. And what we know about this location 2 is that when you have air surrounding a jet of water, there's no pressure in the water. Even though there is pressure inside the tank, as soon as the water goes out, there's no pressure there. And so P2 is 0, P1, if this is location 1, is also 0. And so we've just got some delta z, and then there's a velocity at 2, which we're trying to find. And the velocity of the water at that tank surface is either 0 if the liquid level is steady, like it was in the lab, or it's falling relatively slowly. And so we neglect it compared to the amount of velocity head that there is in the jet going out. So this was the orifice equation. And we can combine it with continuity to say we want to find out how quickly the mass inside of the tank is declining. And so we would just use mass outflow. So we would have a diameter of this opening, which we could get the area from. The velocity we calculate from the Bernoulli equation, the orifice equation. So now we've got a volumetric flow rate, and if you know the unit weight or density of the fluid, then you can find it in mass terms. So in our next class period, we're going to start doing some calculations related to how quickly is the water level going to be changing, because as you know, as h decreases, so does the velocity out. So it's a nonlinear relationship between how tall is the water height and how quickly the water is coming out. For today, though, what we're going to finish talking about is a little bit more wastewater treatment. I just couldn't resist. Here is a schematic of a typical wastewater treatment plant. And there are some elements here, like you think about, it's right before lunch, so think about wastewater. Think about what's in it and what has to be removed, right? Well, yeah, exactly. Yeah, that's why I'm bringing it up. The first step is called a bar rack, and someday I hope you'll get a chance to visit a wastewater treatment plant. There's one here in Huntington that's really actually a pretty great tour. You do not want to go, yeah, right, it's over on the west side. You do not want to go into the room that has the bar rack as you're, like, it smells really bad. That's the worst place in the whole treatment plant is here. It's mainly meant to remove any solids that if they were left to go downstream could cause damage to pumps. So like wedding rings, coins, basketballs. You'd be amazed the sort of stuff that turns up in treatment plants. So the bar rack is actually just like a physical screen that removes really large particles. The second thing is a grit chamber. And something that we talk about that is related to fluid mechanics when we get into environmental engineering is little pieces of sand that if you left it in there, it could really cause a lot of erosion and scour inside of pumps and pipes. So we have to remove that early on. And so it's kind of interesting to calculate how quickly do sand particles settle down through fluids. It's related to the viscosity of the fluid, the diameter of the particle, the shape of the particle. So that's kind of an interesting fluid mechanics application that you'll get to later on down the line in order to design the required size of a grit chamber. The next step here in step 3 is a primary clarifier, which is just to remove the solids that will either settle to the bottom or will float to the top, meaning suspended particles that are a different enough density that they'll float or sink. And then later after that is a really complicated process, activated sludge, that is meant to remove dissolved pollutants. But in between, you can hardly see it because that doesn't project blue very well. At some facilities, they will put a step between 2 and 3, which between the grit chamber and this first clarifier, they'll have a flow equalization basin. Here's a picture of some of my students back in the UAE when we visited a sewage treatment plant in Dubai. They were really jazzed up to be at the sewage treatment plant. I mean, that is unrestrained joy on their face that we got to go to the treatment plant. Yeah, I think they were happy because the tour was over. So, all right. Flow equalization is because you think about how is water used. At night, people don't use as much water as we do at 6 p.m. Why do you suppose that is? Why do you suppose that water demand and therefore the flow of wastewater into a treatment plant, because there's a really direct correlation between how much water gets used from your faucet to how much water is going down the drain. Why do you suppose it follows this pattern? What could explain it? Yeah, people are sleeping, don't take showers at 3 a.m. There's still a little bit of wastewater coming into the network because there are cracks in the pipe that groundwater seeps into. There are some people who maybe have set their dishwasher on a 3-hour delay and so it's going at night, or people who do work the night shift and they're taking an early shower or whatever. So it never goes down to zero. But depending on the city size is a factor too. You know, like a city such as New York City that's never sleeping and really large population and spread out geographically, they would see less of a variation than this. Really small towns are the ones that have huge variations where maybe everyone works at the same mine or the same factory and they're all getting off work at the same shift and they're concentrated area. Then you'd have huge variations. But that's really bad for the bacteria that live in a treatment plant. The bacteria, they do a great job, but you can't give them tons of food one moment and hardly any food the next. You kind of have to feed them in a more steady loading. And so one application of these continuity relationships we've been talking about is the sizing of a basin, so that you've got a big storage tank, and during the day that storage tank is filling up with excess wastewater that's too much for your treatment plant downstream to process. And then at night, when you'd have low flow rate and the bugs would be getting hungry and being less efficient because all of a sudden they're being starved, it's better for us to release some of the water in that flow equalization basin so that we can achieve something closer to the average daily flow. So we'll do an Excel spreadsheet in environmental engineering where we look at how big should a flow equalization be so that we steady the inflow and the outflow. And more immediately, in the project that you'll be taking in hydraulic engineering next semester, we'll do the reverse of that, which is a water storage tank, where you have a varying outflow but a steady inflow. So it's the same kind of idea of breaking this up into hourly pieces and looking at flow in versus flow out, and then that tells you the required size of the tank. Now, just to finish up, on Tuesday I told you about the hydrology course that I teach. They're not going to be offering that next semester. They decided to offer it in the fall, and then there may be a handful of seniors who take a graduate hydrology course that I'll be teaching in the spring. So For those of you who are interested, I hope you'll still be interested next fall, and maybe some of the rest of you will have the time in your schedule to do it then as well. But just wanted to let you know, it looks like that is not going to be on the books. So that's it for today. Let's take one final look at these announcements here. You've got a homework due on Tuesday. On Monday, you'll be trick-or-treating. So do your homework before then, right? All right. Have a good one, guys.